Welcome back to the deep dive. Today we're doing something a little different. We're undertaking a mission that's, well, it's less about the cars themselves and more about a massive national industrial strategy.
That's a great way to put it.
You, our listener, have given us this incredible blueprint. It's an in-depth, really high-level analysis of China's vehicle energy-saving technology roadmap, what they're calling RoadMap 3.0.
Hmm.
So think of this as us dissecting a major consultancy report, really focusing on the mechanics, the metrics of a plan that's designed to completely transform the world's largest auto market.
And that framing is absolutely essential.
Yeah.
We aren't just, summarizing a few tech trends here. We're performing a strategic review. The source material itself calls this a systematic engineering project.
A systematic engineering project. I like that.
It is, and it's foundational. Foundational to their national energy resilience, to reducing reliance on imported fuel, and of course to meeting those really challenging dual carbon goals for 2060. So the mission for us today is to trace this precise, phased, and very quantitative roadmap. It's a plan intended to establish global leadership in vehicle energy efficiency by 2040.
Global leadership. That's the key phrase. It's not just about improvement, it's about dominance.
Explicitly.
And to manage something on this scale, you can't just wing it. You need an architecture. So when we talk about energy saving, it's not just one new battery or a slightly better engine. It's about system efficiency. What's the fundamental structure here?
The structure is built on what they call the 5 pillars of vehicle energy saving. This is the technological architecture for the whole of RoadMap 3.0.
Yeah.
Everything we discussed today, every target, every innovation, it all falls under one of these 5.
So let's list them out.
So number 1, lightweighting. That's pretty self-explanatory. Reducing the overall vehicle mass through new materials, better design.
Got it.
Number 2 is low drag. Basically aerodynamics, making the car slip through the air more easily.
Right.
3 is low friction. This is about minimizing all those small mechanical losses in the bearings, the brakes, anything that rotates.
The invisible energy thieves.
Exactly.
Yeah.
The number 4, thermal management. This is a huge one. Precisely controlling heat, especially for batteries and for cabin comfort.
Critical for EVs.
Absolutely. And finally, number 5, energy management. You can think of this as the brains of the operation. It's the sophisticated software layer that uses AI, data, prediction, all of it, to orchestrate the entire system for maximum efficiency.
That architecture really makes it clear this is a whole vehicle, holistic approach. And one of the first things that stands out in this new Roadmap 3.0 is a change from the last one. They've stopped separating vehicle types.
Exactly. Roadmap 2.0 tended to compartmentalize things.
Yeah.
You'd have a strategy for traditional combustion vehicles and then a separate one for new energy vehicles, or NEVs. Roadmap 3.0 unifies that vision. It recognizes that technologies like, say, low friction or advanced thermal management, they're universal.
Yeah.
They drive efficiency no matter what the powertrain is.
Yeah.
Pure EV, hybrid, even an advanced gasoline engine can benefit.
And with that unification comes a new level of rigor, right? The introduction of detailed quantitative segmentation.
Yes, and this is the hallmark of a serious strategic plan. They've moved away from these sort of fuzzy industry-wide goals. Instead, they introduce model grading. So for passenger vehicles, you have A-Class, B-Class, C-Class. And for commercial vehicles, they define these detailed, typical application scenarios.
Like a heavy truck doing long-haul freight versus a light truck doing city deliveries.
Precisely. And this segmentation is absolutely crucial because, comparing the efficiency of a little A-Class EV to a huge luxury C-Class SUV, it's meaningless.
It's apples and oranges.
It is. So now, progress can be measured precisely using very clear KPIs that are tailored to the vehicle's size and its job.
That kind of precision is what allows an entire industry, from the company making the steel to the one writing the software, to align their R&D toward the same measurable targets.
It creates an actionable strategy. For commercial vehicles especially, this is a game changer. They operate in such varied roles. Now, you can set reduction percentages relative to their 2024 consumption baseline, which ensures the targets aren't just theoretical, they're commercially viable for that specific job.
Okay, so let's unpack this. Before we look at the next 15 years, the sources give a pretty candid assessment of where they are right now based on the last roadmap. And it's a mixed picture, a story of early triumphs followed by a kind of stagnation.
The initial momentum was undeniably strong. The assessment confirms that most of the goals they set for 2025 were actually met or even exceeded by the end of 2024.
Ahead of schedule.
Way ahead. It shows that when you have clear regulatory guidance and fierce market competition, the industry can move incredibly fast.
So where were the biggest wins? The numbers for lightweighting? They really jumped out at me.
Lightweighting was a huge success story, and it was driven primarily by the need to offset the massive weight of battery packs in EVs.
Of course.
For compact, pure EVs, the lightweighting coefficient, that's a measure of how efficiently you remove weight while keeping strength, it dropped by a staggering 29% compared to 2019.
Wow, 29%. And the original target was what, 15?
Just 15%. So this wasn't just some incremental improvement. It was a foundational shift in how they build cars.
To nearly double the efficiency gain like that, it suggests huge breakthroughs in materials, structure, and process. They didn't just swap out steel for aluminum.
No, they redesigned the vehicle from the ground up, around the power source. The accelerated adoption of ultra-high-strength steel, complex aluminum alloys. And the second major win was in thermal management.
Ah, the range anxiety killer, especially in winter.
That's the one. The widespread adoption of high-efficiency heat pump systems is basically the standard now. The source material notes these systems are saving more than 35% on energy compared to the old PTC electric heaters in cold weather.
Right, the PTCs are just giant toasters, really. They just burn through the battery.
That's a perfect analogy. Heat pumps are way more complex, but they just move existing heat around.
Yeah.
Achieving that 35+% saving blew past the 25% target and really addressed a massive consumer pain point about cold weather range.
And the third big win, low drag, gave us some pretty stunning numbers. We've seen mass-produced cars now with aerodynamic coefficients, the seed of like 0.255, and some of the Pioneer vehicles are pushing below 0.20.
Which is approaching the territory of high-performance race cars. The urgency is simple. Every single point you shave off that C value translates directly into more range, and range is the ultimate currency for an EV maker.
So, okay, here's where it gets paradoxical.
Yeah.
If the tech is advancing this quickly, beating all these targets years ahead of schedule, why does the assessment show that the overall industry's average energy consumption has basically hit a plateau, a market shift plateau, they call it?
This is the critical finding. This is the whole justification for the sweeping changes in RoadMap 3.0. The data shows that the average energy consumption for pure EVs, measured across the whole fleet, actually went up. It went from a low of 12.24 kilowatt hours per 100 kilometers in 2021 to 12.49 by late 2024.
That's completely counterintuitive. How can all the individual technologies get so much better, but the fleet average gets worse?
It's a classic case of market preference, just steamrolling engineering gains.
Yeah.
The main reason is the dramatic shift in what people are buying.
Bigger cars.
Bigger cars. A few years ago, the market was full of smaller, lighter A and A-class vehicles. They naturally get the best efficiency numbers. But as the market matured, consumers shifted sharply toward bigger, heavier B and C-class models.
SUVs, executive sedans.
Exactly. More luxurious, more space, but they require a lot more energy to move.
So the engineers are making, say, a B-class SUV way more efficient than it was 5 years ago. But because the average person is now buying that B-class SUV instead of an A-class hatchback, the overall industry average looks worse.
Precisely. The consumer's demand for size and luxury is effectively canceling out years of incredible engineering progress. You see the same thing with plug-in hybrids, the PHEVs. Their average fuel consumption rose to 6.2 liters per 100 kilometers in 2023, mostly because people are buying huge PHEV SUVs.
This makes the whole task so much harder. The efficiency targets aren't a fixed goalpost, they're on a treadmill. The engineers have to run faster and faster just to keep the average from getting worse because of market demand.
That's right. And it's not the only headwind. The roadmap also identifies two more problems, which it calls the paradoxes of progress.
Okay, let's start with the first one. The intelligence paradox.
The intelligence paradox highlights the hidden energy cost of turning your car into a supercomputer on wheels.
Right.
All this push towards intelligent cockpits, advanced driver assistance systems, ADAS, and eventually full autonomy, it requires massive computational power.
You're talking about high-end domain controllers, specialized AI chips, plus all the sensors, LiDAR, multiple radars, cameras. They all need constant power.
And that power draw is significant. It's not trivial. The assessment estimates this extra equipment adds somewhere between 5 to 10% to the vehicle's overall energy consumption.
So you can make the powertrain 10% more efficient, but if the car's brain eats up that 10% gain, you've gone nowhere.
You haven't moved the needle at all. And this implies a fundamental shift in how we even define energy efficiency. Historically, it was all about propulsion, how much energy gets to the wheels. But now the focus has to be equally on the efficiency of these auxiliary systems.
You have to learn how to compute efficiently.
Exactly. The roadmap calls this out directly. It says future standards for intelligent driving must assess and regulate this auxiliary power consumption.
And the second paradox is related, the performance paradox.
This one is driven by the consumer demand for, thrilling performance, ludicrously fast acceleration, high-speed stability, even novelty features like doing a tank turn in place.
Right. And these features often require more complex motor setups.
They do. They rely on sophisticated multi-motor distributed drive architectures. So you might have an independent motor for each wheel or each axle. It's brilliant for vehicle dynamics and control.
But it's less efficient than one single centralized motor.
Correct. A distributed system inherently has more losses. Power distribution, conversion, just coordinating all those smaller units. It results in about a 10% increase in energy consumption compared to a simpler centralized drive. So the challenge is twofold. Make these systems lighter and cheaper, and make the motors and power electronics themselves more efficient to close that gap.
So to sum it up, RoadMap 3.0 isn't just about hitting numbers. It's about solving these two paradoxes while fighting the market trend towards bigger cars, all without losing overall efficiency. That is a monumental task.
It's a huge undertaking.
So that context perfectly sets the stage for the 2040 vision. We're talking about a multi-decade plan to solve all this and achieve explicit global leadership. What's the overarching strategic framework for this transformation?
The long-term vision is, it's to transform the entire industry toward this ideal of highly efficient, intelligent green mobility. And that culminates in global dominance by 2040. The sources define two core interconnected strategies to get there, which we can think of as a hard-soft twin drive.
Okay, twin drive. Let's break down the hard component first. High-efficiency design drives ultimate energy savings.
This driver is all about the relentless pursuit of perfection in the physical world. It's the continuous optimization of those 5 pillars we talked about.
Right.
It means pushing material science to its absolute limits for lightweighting, streamlining shapes until they're almost frictionless for low drag, perfecting every moving part.
Yeah.
But, and this is critical, the hardware has to be designed from day one to be optimized by the software. It's about squeezing every last possible joule of energy out of the physical car.
And then the second driver, the soft part, deep intelligence drives industrial integration. This is where they look beyond the car itself.
This is the big strategic pivot. This is how they plan to overcome that efficiency plateau and the intelligence paradox. It's an admission that just making the hardware better and better has diminishing returns. It gets too expensive. So the next big scalable leap in efficiency has to come from integrating the vehicle with its entire external ecosystem. It means accelerating the convergence of the auto sector with energy grids, with transportation networks, with AI infrastructure. And the ultimate goal is the large-scale application of the Vehicle Road Cloud integrated system.
The VRC system. So instead of just competing on who builds the best car, the competition shifts to who can build the most efficient traffic ecosystem.
That's exactly. The VRC system can unlock efficiency gains that are just impossible for a standalone vehicle. If you can coordinate traffic flow, predict optimal speeds across an entire city network, maximize energy regeneration across a whole fleet of cars, you're not just optimizing a product anymore. You're optimizing the entire system's throughput.
And that turns the intelligence paradox on its head. The massive computing power is no longer just a cost. It becomes the key to a huge competitive advantage.
Precisely.
So let's talk numbers. What are the actual finish line markers? What defines global leadership in 2040?
The targets are, well, they're breathtakingly aggressive, especially when you look at where we are today. For passenger cars, the top-tier, industry-leading, pure EVs are aiming for an ultra-low energy consumption of 7.5 kilowatt hours per 100 kilometers.
7.5. Let's just pause on that. The industry average today is around 12.5. The most efficient A-class models might hit 10.0 by 2030. Getting from, say, 9.0 down to 7.5, that requires some radical integrated breakthroughs that we haven't even industrialized yet.
It requires near-perfect synergy between all 5 pillars. It's the absolute peak of efficiency. And for hybrid vehicles, the 2040 target is to get fuel consumption down to 2.6 liters per 100 kilometers.
Wow.
Which implies an incredibly efficient powertrain, where the combustion engine is almost always operating in its perfect efficiency sweet spot, supported by super effective energy regeneration.
And what about the commercial vehicle fleet? That's really the key to the national carbon reduction goals.
For CVs, the targets are set as percentage reductions from their 2024 baseline, because the segments are so diverse. By 2040, traditional energy commercial vehicles need to cut consumption by over 20%, pure EVs by over 17%. But the most aggressive targets by far are for hybrid commercial vehicles. They have to achieve an energy reduction of over 38%.
38%. Why are the hybrid CV targets so much higher than the pure EV ones?
It's because the initial technological gap is wider, which, creates the biggest opportunity for quick gains. Heavy-duty transport often involves high loads, frequent stop-start cycles.
Perfect for regenerative braking.
Perfect. Regenerative braking and battery assistance can provide massive immediate efficiency gains over a traditional diesel engine in those conditions. So that aggressive target really confirms this strategy. Rapidly electrify the heavy-duty sector with hybridization in the near and midterm, while the infrastructure for pure EV heavy transport matures.
So hitting these targets isn't going to happen overnight. The roadmap breaks the next 15 years into 3 distinct phases. Before we dig into the metrics, maybe we should quickly clarify the testing cycles we keep mentioning: WLTC, CLTC.
That's a great point. These targets are all measured against specific standards that simulate driving. So WLTC is the Worldwide Harmonized Light Vehicles Test Cycle. It's generally used for hybrids and gasoline cars, and it's meant to reflect more realistic dynamic driving.
Okay.
Then you have CLTC, the China Light Duty Vehicle Test Cycle. This is often used for pure EVs. It has lower average speeds, less aggressive acceleration, so it's generally a bit more forgiving for range estimates.
And for trucks?
That's CHTC, the China Heavy Duty Commercial Vehicle Test Cycle. It's specific to trucks and buses and reflects their unique loads and driving patterns.
Okay. Understanding those standards really helps. So let's start with the near future. Phase 1, from 2026 to 2030.
The focus here is on industrializing and scaling up the key technologies that have already proven successful in those pioneer models. It's about taking things like integrated low-drag design, wide temperature thermal management, and integrated lightweighting, and making them standard practice across all new vehicle platforms.
So taking the breakthroughs and making them mainstream, what are the hard targets for passenger cars in this phase, say for the most efficient A-class segment?
For an A-Class pure EV, the target drops to less than or equal to 10.0 kilowatt-hours per 100 kilometers on the CLTC cycle. That's a pretty significant tightening. For A-Class hybrids, the target is 3.1 liters per 100 kilometers. And even traditional gasoline A-Class cars have to hit a strict 5.0 L100 kilometer target.
So they're still pushing for internal combustion engine optimization even while they electrify?
They have to. And for commercial vehicles, this is where you really see that aggressive focus on hybridization.
Right.
A traditional heavy truck has to achieve a 13% energy reduction from the 2024 baseline. But a hybrid heavy truck, it has to push for a reduction of over 24% by 2030.
That is a striking difference.
It confirms that hybridization is seen as the low-hanging fruit. It's the immediate lever they can pull to cut massive consumption in the logistics sector before the heavy EV charging infrastructure is fully built out.
Okay, moving on to the second phase. Midterm goals. From 2031 to 2035, this is where the strategy pivots from just hardware optimization to deep integration.
This period is all about breakthroughs in intelligent energy saving. It's the transition from a predictive phase to a fully coordinated one. The core goal is to achieve deep fusion between all the different systems.
So integrating thermal management and high-level autonomous driving directly with the central energy management system.
Yes, so the vehicle's energy use isn't just dictated by the driver anymore. It's being dictated by real-time sensor data, by route prediction. If the ADAS system sees a traffic jam a mile ahead, the energy management system should already be adjusting the battery's thermal needs or the powertrain allocation.
So you're turning the cost of intelligence into an efficiency asset.
That's the idea. Quantitatively, the targets keep dropping. A-Class pure EVs are now aiming for 9.5 kilowatt to 100 kilometers, and hybrids are tightening to 2.8 L100 kilometers.
And the commercial vehicle targets show another huge jump in required efficiency.
They do. By 2035, traditional heavy trucks need to hit a 22% total reduction. But the hybrid heavy trucks, they're being pushed to over a 35% reduction compared to the 2024 baseline.
And finally, the strategic summit. Long-term goals, 2036 to 2040. This is where that whole vehicle road cloud ecosystem comes into full effect.
Right. The focus here is on multi-vehicle collaborative control. It's about taking the optimization loop out of the individual vehicle and integrating it into the city, the highway, the whole logistics network.
And the final metrics represent those last, incredibly difficult margins of efficiency.
They do. The A-Class EV target tightens one last time to a 9.2 kilometers, 100 kilometers, and hybrids hit that ultimate goal of 2.6 L100 kilometers. For commercial vehicles, they hit their strategic goals. Traditional heavy trucks at over 27% reduction, and the hybrid trucks soar past a 41% reduction from the 2024 baseline.
41%.
And that comprehensive reduction across the heavy-duty fleet, that is the national-level strategic win that underpins this entire document. That's millions of tons of carbon saved every year once the fleet turns over. That's the real driver.
Okay, now for the core of this deep dive. Let's get into the actual technical mechanisms that will make all these ambitious goals possible. We need to go into detail on the innovations within each of the 5 pillars. Let's start with lightweighting, where the sources talk about a triple path: materials, structure, and process.
Lightweighting is the foundation. Every single kilogram you save reduces the energy you need to accelerate, to brake, to just maintain speed. So the materials focus is on high strength, but also cost-controlled solutions.
For example, they talk about demanding hot-formed steel with a tensile strength over 2.2 GPa. That sounds extremely high. Why is that specific number so important?
2.2 gigapascals is well into the ultra-high strength steel category. Its importance is about safety and mass reduction. Using steel this strong allows you to use much thinner and therefore lighter panels and structural parts without compromising crash safety.
And what's the technical challenge in making it?
It's all in the manufacturing process. Hot forming needs incredibly precise temperature control and then rapid quenching to create that specific microstructure, and then forming it into a complex car part like an A-pillar without introducing microcracks. It's a huge industrial hurdle. It requires very sophisticated automation and quality control.
And beyond steel, there's a heavy focus on aluminum and magnesium.
Yes, and the goal here is to move beyond just simple substitution. They want breakthroughs in high-strength, high-toughness aluminum alloys, and especially in aluminum-steel hybrid connection techniques.
Right, because you can't just weld aluminum and steel together easily.
Not at all. They have different electrical potentials, which leads to galvanic corrosion. It's a nightmare. So developing reliable, high-volume joining processes like friction stir welding or advanced adhesives that will hold up for 15 years is absolutely essential to building these mixed material bodies efficiently.
And structurally, you can't talk about weight without talking about the battery.
It is the single heaviest component, so integration is everything. The roadmap emphasizes deep integration of future full, solid-state batteries directly into the vehicle chassis or body.
Cell to chassis, that kind of thing.
Exactly, cell-less structural component. It eliminates all the redundant battery casing and surrounding structures, so you're maximizing the use of that mass.
And what about the processes to actually mass produce all these complex, lightweight parts?
The sources highlight a big push for automated large-scale die casting. You can replace dozens of smaller stamped and welded parts with one complex casting. And also high-efficiency forming processes to work with things like continuous carbon fiber composites to try and bring those materials down from supercars into more mass-market vehicles.
Now, for commercial vehicles, the targets are incredibly specific. Heavy trucks are aiming for a 500-kilogram weight reduction by 2040. How does that break down?
That 500-kilogram target is spread across the whole vehicle chassis, cabin, powertrain. And the projection is that this reduction alone will yield a 0.65% energy consumption reduction.
Which sounds small.
It sounds small, but you multiply that across a national fleet of trucks covering millions of kilometers a year, and it's a massive fuel saving. The materials goal is specific, too. Increase high-strength steel use in chassis frames to 75% and in driver cabs to 60%.
Okay, let's move to pillar 2. Low drag, aerodynamics. We've seen pioneer cars getting close to the theoretical minimums, but the roadmap suggests there's still more to gain through new design philosophies.
There is. For passenger cars, the future is what they call platform-based, intelligent, and collaborative design. We're moving away from just optimizing one component, like a spoiler or a mirror.
Right.
Instead, it's about optimizing the multi-component coupling effects of the entire vehicle platform. The tires, the wheels, the underbody, the cooling vents, the main body shape, they all had to be designed simultaneously to manage airflow as one seamless system.
The integration of intelligence here is really fascinating.
This is where AI really comes into the design studio. The roadmap calls for AI optimization algorithms that can just search the entire design space for optimal aerodynamic shapes, way faster than human engineers could ever iterate through prototypes. And then this connects to active aerodynamic systems.
Smart grills, adaptive spoilers.
Exactly. Devices that are linked to real-time traffic and weather data. If you're driving fast on a highway, the system might close a vent to reduce drag. If you're stuck in city traffic, it opens it for better cooling. It optimizes drag on the fly.
And the targets reflect this push. They're aiming for a sea of 0.17 for an EV sedan and 8.23 for an EV SUV by 2040. Those are unbelievably low numbers for mass-market
Say
vehicles.
they're world-beating. Hitting 0.17 requires a complete rethinking of the vehicle shape. It's pushing cars into the realm of hyper-efficiency.
But the story for commercial vehicles is completely different, isn't it, because of non-technical hurdles?
This might be the single biggest non-technical constraint in the entire roadmap. The traditional truck shape, that short, vertical, flathead cab, is an aerodynamic disaster.
It's a brick.
It's a brick. And it's that way because of length regulations that are designed to maximize cargo space. And this just fundamentally limits what you can do with drag reduction.
So even though we know that long-head, aerodynamically optimized trucks are more efficient, operators won't use them because they lose valuable cargo space.
Exactly. The source material explicitly says there is a long-term necessity to achieve regulatory exemption for these longer aero-optimized cabs. Until that policy changes, the CV roadmap is focused on just making the brick as slippery as possible.
So better integrated cabs, streamlining the cargo boxes, reducing the gap between the cab and the trailer.
All of that. And even with those constraints, the 2040 targets are aggressive. A seed of 0.35 for a flathead heavy truck. But if, and this is a big if they get that regulatory exemption for long head designs, the target drops to 0.31.
So one policy change could unlock years of efficiency gains overnight.
It shows you the size of the regulatory lever they could pull.
Okay, pillar 3, low friction. This is about tackling those constant, invisible parasitic losses in the brakes, the bearings, the drivetrain.
This is the pursuit of those marginal gains that really add up. For passenger cars, brake caliper drag is already pretty good, near international best-in-class. But for heavy trucks, low-friction caliper tech is still pretty immature. It's a major R&D focus.
So what's the goal for passenger car brakes?
The ultimate goal is a zero-drag brake caliper design. This means that when the driver lifts off the pedal, the system has to completely release pressure so the pads aren't even fractionally touching the rotor.
Which is huge for maximizing coasting and regeneration in an EV.
Absolutely. The 2040 goal for a single-piston caliper drag torque is an ultra-low here of 0.5 newton meters. This is just pure precision engineering. Same for wheel hub bearings. They're demanding high-precision seals and high-performance, low-viscosity grease.
And what about the huge reductions needed for heavy trucks?
The components are so much bigger, so the friction is greater. For heavy truck pneumatic calipers, they have to cut the drag torque in half, from 7 newton meters in 2030 down to old-on 3.5 by 2040. They're also targeting intelligent wheel ends with sensors that can manage friction dynamically.
And I imagine truck tires are a massive focus, given their weight.
The biggest parasitic loss for a truck at speed is rolling resistance from the tires. The target is ambitious, to drop the heavy truck tire rolling resistance coefficient from 5.0 parts per thousand today down to 3.8 by 2040. That requires huge breakthroughs in tire construction and materials.
Okay, let's move to thermal management. This addresses that key challenge, maintaining EV range in extreme temperatures, because current heat pumps really struggle below -10 degrees.
This is maybe the single biggest bottleneck for EV adoption in cold climates. When that heat pump gives up, the car switches to that battery-draining resistive heating we talked about. The solution outlined is a wide temperature capability, and that demands some specific tech breakthroughs.
What's the key technology that lets a heat pump work efficiently at, say, -20 degrees C?
The roadmap points to two big innovations. First is new, high-efficiency, eco-friendly refrigerants, and second is something called vapor injection booster technology.
Vapor injection, can you break down what that actually does?
So think of a heat pump as moving heat from the cold outside air to the warm inside cabin. When it gets really, really cold, the refrigerant struggles to absorb enough heat from that frigid air.
Right.
Vapor injection uses an auxiliary circuit to inject a small amount of high-pressure refrigerant vapor directly into the compression cycle. This basically boosts the density and the mass flow rate of the refrigerant. By boosting the energy in that compression stage, the heat pump's capacity and efficiency are dramatically improved, letting it pull heat from the air even when it's -20 degrees C or colder.
So it's a technical fix to dramatically extend the heat pump's operating range, and at the same time, they're pushing for more system integration.
Yes. The trend is towards these ultra-efficient integrated modules that put the compressor, valves, and heat exchangers all into one compact unit. This saves space, weight, and reduces fluid resistance from long pipes. They're also looking at phase change materials to store waste heat from driving and use it later to precondition the battery or cabin.
And then there's the final layer on top of that, intelligent control.
This is where AI and model predictive control come in. The system stops being reactive and becomes proactive. It uses navigation data, traffic conditions, even your driving habits to predict thermal needs minutes in advance.
So if the GPS knows you're about to get home and plug in, it might start preconditioning the battery for charging during the last mile of your trip.
Exactly, and the 2040 target for this is stark. Reduce the average A-class AC power consumption at -20 degrees C to 1400 W. That's a huge efficiency gain over current systems.
It requires total coordinated control of every heat source in the car, battery, motor, electronics, cabin, all as one cohesive ecosystem. Which brings us to the final, orchestrating pillar, energy management. This is the brain behind that hard-soft twin drive strategy. The roadmap outlines a three-phase evolution here.
Phase 1, from now until 2030, is about establishing predictive energy management. This is the first layer of intelligence.
How does that predictive part work in real time?
It uses high-def maps, GPS, and V2X information to forecast the energy demand for your entire trip. The car knows if a steep hill or a long downhill is coming up, so it can optimize the powertrain in advance. For an EV, it might manage the battery charge to maximize regeneration on that downhill. For a hybrid, it ensures the engine only runs at its peak efficiency.
And the sources say this is already effective.
They do. This first layer alone can save 5 to 15% for passenger cars and a measurable 3 to 4% for commercial vehicles. This tech is basically reaching maturity now.
Then phase 2, from 2031 to 2035, elevates this to deep fusion.
Deep fusion is the mandated convergence of all these separate intelligent systems. It's about integrating the energy management system, the thermal management system, and the high-level intelligent driving systems like L3 plus autonomy. This is how you solve the intelligence paradox.
So if they're all fused, they can make decisions that benefit the whole system, not just their one little domain.
That's it. For example, the ADS sensors see that traffic is stopping suddenly ahead. The energy management system instantly maximizes regeneration, while the thermal system knows the motors will cool down, so it adjusts battery preheating. This coordination unlocks substantial additional savings, potentially 7 to 20% more for passenger cars.
And finally, phase 3, 2036 to 2040, the strategic peak vehicle road cloud integration.
This is the ultimate goal. It transforms the whole approach from optimizing a product to optimizing a system. It uses advanced communications, CV2X, 5G, 6G, to coordinate multiple vehicles and traffic infrastructure across a huge area.
So instead of one car trying to drive efficiently, the whole traffic network is optimized.
Exactly, and the payoff is huge. First, you reduce all the systemic waste, like unnecessary stops and starts. You can coordinate speeds to hit green lights or organize trucks into automated platoons to drastically cut aerodynamic drag. And second, you reduce the need for every single car to have peak hardware performance to deal with chaotic traffic.
And the savings.
The sources estimate this VRC system could provide a further 10 to 14% energy reduction for passenger cars and up to a 9.5% total reduction for commercial vehicles. And they're planning to start this in controlled environments like ports and mines before they scale it up to cities.
It's a fascinating progression, from better hardware to onboard intelligence to finally ecosystem intelligence.
It's the strategic path to get past that efficiency plateau. The easy gains are gone. The future has to be coordinated.
So we've completed this pretty comprehensive review. We've covered everything from material science with 2.2 GPA steel to future connectivity with 6G traffic platooning. If you just step back and look at the entire arc of this plan, what's the key message about the sheer magnitude of change being mandated here?
This roadmap is not a list of suggestions. It is a mandate for a complete, foundational re-engineering of the automobile. It's targeting double-digit consumption improvements in nearly every vehicle segment. The scale is monumental, it affects deep manufacturing supply chains, and it demands rapid, simultaneous maturity in AI and control software.
It's a deliberate state-led effort.
It is a state-led effort to achieve strategic decoupling from fuel dependence while establishing undeniable global leadership in high-efficiency mobility tech.
And when you synthesize all of this, especially focusing on the challenges from the intelligence and performance paradoxes, what does it tell you about the core strategic shift that's required for them to succeed?
It tells us that the future of competition is moving beyond the single vehicle. The paradoxes are proof that just making hardware marginally better is too slow, too expensive, and too easily canceled out by market trends. Therefore, the next major scalable leap in energy saving must come from that external intelligence, the vehicle road cloud ecosystem control. The roadmap demands that hard-soft twin drive. The best material science is useless without the best AI orchestrating how it's used.
So what does this aggressive timeline mean for global competitors trying to keep up?
It creates a massive strategic challenge for them because this roadmap is based on achieving technological integration at a system level, not just component parity. A competitor can copy a heat pump design or use a similar steel alloy, but they can't easily replicate the efficiency gains that are locked inside a citywide VRC ecosystem, which requires aligning telecom, infrastructure, and energy sectors under one single goal. It shifts the competitive arena from product innovation to industrial integration.
That is a perfect synthesis of this entire plan. To wrap up this deep dive, let's leave you, our listener, with one final provocative thought that really emerged from the source material.
We spent a lot of time detailing how aerodynamic constraints, specifically those regulations that force commercial vehicles to use inefficient flathead cabs, are severely hindering energy saving, even though the technology for better long head shapes already exists.
Right, it's a massive non-technical hurdle.
It is. So the thought is this. If future policymakers grant the necessary length exemptions for these aerodynamically optimized commercial vehicles, allowing the transport sector to finally transition to the much more efficient long head designs, how drastically could that single non-technological policy shift accelerate the entire commercial transport sector toward, or maybe even past, its aggressive 2040 energy reduction goals?
It suggests a legislative decision, not an engineering breakthrough, holds the key to the next great leap in logistics efficiency.
A massive regulatory lever just waiting to be pulled.
A truly fascinating point on how policy can unlock physics. That's all the time we have for this edition of the Deep Dive. We hope this roadmap offers you a clearer, more detailed picture of the technological and strategic journey to 2040.